Okay, so let's start. So during the last couple of years, we had many interesting developments in the video coding field. And actually, the purpose of this talk is to provide you with some technical observations regarding the most recent versions of the most popular codecs in order to assist you in your decision-making process for selecting the right codec for your specific needs. So I will briefly go over the agenda. So first of all, I will provide motivation for the study, followed by a brief introduction into VVC and HEVC video coding standards, as well as introduction into AV1. We don't have much time, so I will do it quite briefly. Then I will briefly overview the selected test candidates, followed by detailed experimental results, and finally I will provide a summary and conclusions. So, as we all know, currently many video codecs and their performance is constantly changing, right? So we need to constantly clarify it. This is a constant process. What are the most deployed codecs today? So we have AVC, which was approved 2013, and even after 20 years, it's still the most deployed codec today. We have HEVC, approved 10 years ago, and its actually deployment drastically increased during the last couple of years. We have H.262 MPEG-2, which is still mainly used for broadcasting. We have VVC, which actually is the most recent video coding standard developed by Javid. And we have AV1, which is being developed by AOM as substitution to video coding standards. Now, Javid established a joint group between VKK and MPEG in 2017, and just something like 2 years later, we got the first version of standard, which was called VVC version 1. Currently, we have also the second version, which mainly contains range extensions, also new level 6.3, and some additional things, beneficial things. So, about the specific VVC technical features, the features are really, there is a really long list of features. We don't have time to go over them, but what is worth to mention that it has quad tree, similarly to what has HEVC, but in addition, there are so-called recursive binary and ternary splits. You can see in green and red lines here. In addition, it has a lot of different tools, such as reference picture resampling. What is worth to know is cross-component linear model. It has also wide angular interprediction modes, up to 85 directional modes, compared to only 33 in HEVC. It has a thin motion compensated prediction, which is actually based on the fact that natural videos has rotation, zoom, and additional features. We have also a nice tool which is called geometric partitioning, which actually interesting because it performs the coding based on the geometrical split across the block and also provide additional gain. I will go fast to the next slide, which is actually a brief introduction of HEVC. Everybody is well familiar with HEVC, so just worth to mention that currently HEVC has already 8 versions. The last version was established in 2021, and it includes additional SCI messages on top of existing solutions. Now, about some specific technical features, we have quad tree partitioning tool, which provided most of the gain. We have so-called residual quad tree tool. What is also worth to mention, it has parallel processing. Actually, during the development, it was keep in mind during the whole process, and compared to AVC, it has many tools which allow parallel processing. Now, about AV1. AOM was actually formed 2015, just 2 years after VP9 codec was finalized. The purpose of establishing AV1 actually was to, let's say, to compete with the video coding standard, to provide some kind of alternative to existing solutions. And today we have 3 main versions established. The last one was established 2021. Version 0.3. Today we have, I think, 3.0. Today we have 3.6 or maybe even 3.6 something, 6.5, or I don't remember correctly, but this is the last major change in AV1. Now, about the technical features, it's actually start from the block 128 on 128. It has enhanced directional intra-prediction with 56 directional intra modes compared to 85 in VVC. What is also worth to note, it has additional loop filter tools such as constraint directional enhancement filter, which is a detail preserving filter coming after the deblocking filter. And very nice tool, which is actually worth to introduce, is film grain synthesis tool. This is really, I personally like it very much. It's normative post-processing tool being applied outside the coding loop. So this tool removes the film grain from the video content prior to compressing it, and then film grain is synthesized as a decoder based on the parameter received from the encoder size and added to the reconstructed video. So by such a way, something like 20% gain is achieved, which is quite impressive, I would say. Now, about the test candidates. I selected the most recent test candidates. So we have VTM version 17.0, which is a reference test model of VVC standard. We have VVENC. VVENC is an open source video codec based on HEVC standard, developed by Fraunhofer HHI. An additional test candidate is HM version 17.0, which is a HM test model based on HEVC video coding standard. And we have open source encoder X265 version 3.5. X265, as everybody, it's jumping. X265, as everybody is aware, in my opinion, is the best open source video codec based on HEVC. We actually use it quite a lot. It's developed by Multicoreware. And we have AV1 version 3.6, which is libaOM codec developed by AOM. Now, about the configurations. First of all, we selected random access configuration because it provides better results in terms of coding efficiency. Intra-period was set to 1 second. This is nothing special. This is based on common test conditions also used during standardization. Group of picture was selected to be 16. Why? Because it's actually too much what was kept in mind during the development of HEVC. Generally, also group of picture of 32 and 64 are used, which will allow to providing larger gains. I will explain it further. The rate control for VTM and HM reference software was disabled because they do not have, I would say, the real rate control mechanism. These are single-pass encoders. AV1 was tested in a so-called picture-level quantization mode with the quality level adjusted to fit the bit rates produced by the rest of encoders such as HM and VTM. So here you can see the quality levels. Now, all encoders beyond the test models have been set to 2-pass mode, by the way, also including AV1. So now I would like to say a couple of words about why actually I think that it will be okay to test AV1 in 2-pass mode. Also, by the way, it's somehow related to X265 in VVENC, but for AV1, I think it's more critical. AV1 actually is known not to perform well with fixed QPS encoding structure. And the reason for that, because from the beginning, AV1 didn't have an efficient GOP hierarchical structure. And why? Because it's like, I don't want to get into details related to some specific licensing issues, but it's an alternative. It has so-called altref frames and golden frames, okay? So altref frames can be a composition of future and past frames, and this is somehow similar to hierarchical B-frame structure as we know in video codecs. Now, in addition, altref frames are not displayed, and instead, so-called skip mode is used, and the regular frame, which is not altref frame, uses altref frames as the only reference, is displayed. So it's a little different structure, and also AV1 uses so-called golden frames, and AV1 can select these frames from specific distance in the past. Now, by using these golden frames and altref frames in such a way, AV1 actually mimics the hierarchical structure of video coding standards as we know them, okay? And this process works much better for AV1 in such a structure, and by such a way, by using 2-pass rate control mechanism actually allows AV1 to reach quite nice performance. Okay, so now about the settings, the command line settings, and some of you who want to test it, you can do it by using these settings, are set to the best performance mode. So we can see that VVENC is set to so-called expert mode. This is the best quality mode, which is slower than the rest of the modes. X265 I set to placebo. Now, based on my experience, it can provide some gain because this work is focused mostly on gain and not on complexity. So in my future works, which I'm planning to publish in journals, I actually will test X265 also in very slow and slow modes because this will provide a significant speed up related to placebo. And in addition, AV1 was also set to the best performance with the CPU used equal to 0, quality level set to the levels that I presented earlier, okay? So from this perspective, I would like to emphasize again, this work focused on the best performance, most in terms of quality, okay, and not the complexity. Now, regarding specific sequences, the sequences that I selected are 4K and full HD sequences. You can see them here. These are typical sequences taken out of common test conditions. And here are the results. I want to explain the results, what you actually see here. Now, about the VVC, VVENC, and VTM, you see quite big performance compared to AV1 in the first column. Why? Interesting thing is that VVENC performed actually better in this setting than VTM, okay, by around 10%. Like VTM has a overhead of 10%, and VVENC compared to VTM has a gain of about 8%. Okay, this is actually done by due to the fact that VVENC uses different optimizations, including perceptual optimizations. And in this setup, using GOP of 16, okay, it performs better. In future work, I will extend it also to different GOP sizes, such as 32 and maybe possibly 64, which is, can be used for, especially can be used for UHD and full HD video sequences. Now, also important to notice here that if you compare VTM to HM, you have gain of 34%. The reason that why it's not close to 40 was presented in the previous slides. Again, this is a GOP size. For GOP size of 16, you see the gain lower than it's used for larger GOPs. If you compare HM to X265, you get a gain of 22%, which means that actually X265 is not the actual reference test. Like it's still has room for improvement with this perspective, this perspective of coding gains, and it has overhead of 30% on HM. Okay, so when compared X265 to VVENC and VTM, we have an overhead of more than 100%. I think these are more or less the main key points. Now, if you go to complexity, again, this work is focused mostly on best performance in terms of coding gain, not complexity. But if we look into complexity, we can see that VVENC performs actually faster. Like it's even running faster twice than AV1. It achieves a coding gain of 23% for these sequences, for this setup. VTM, on the other hand, runs around 3 times slower than AV1. If you compare AV1 to HM, it runs slower by around 5 times, but it achieves gain of around 20% based on this slide. And X265, even in this really slow setup with placebo mode, it runs around 5 times faster than AV1 and around 12.4 times faster than VTM. So if you will switch to very slow, I would assume that we will get at least twice faster performance with just a small difference in coding gain, if any, okay? So these are the results with this perspective. On this slide, you can actually see the summary of what was just discussed, okay? You can go over that later. And this is literature review. We'll have 1 minute for questions. Thank you.
Any questions? Well, let's limit it to 1 question.
So I think VVENC might be specifically optimized for the quality metrics weighted PSNR. If we use traditional BD rate, as like Luma BD rate, what's performance?
For the Luma BD rate?
Yeah.
Just for the Luma?
Yeah.
I don't have the result in front of me. I think this is not because of big difference in Chroma and Luma. The difference exists, but it's not so significant. Look, here you have the results in terms of weighted PSNR, which means you take 6 times Luma, 1 times Chroma, and 1 time U, 1 time EV, and divide by 8. So this gain is mostly due to the Luma, okay? Because it's weighted PSNR. It's not, it's weighted PSNR with the 6 time Luma, okay?
Okay. I have another question. So if you disassemble the two-pass coding for everyone, what's performance?
I didn't do it, but I would expect the difference to be significant. For example, for X265, if you disable two-pass coding, you get, the gain varies, but I would expect it to be more than like close to 10% maybe. So I would expect everyone to be the same. Like, I didn't test it directly, but I would expect it to be like 10% at least. Because this is the whole point here that when you use two-pass rate control, it's provide quite nice gain. Even like X265, I used to run even 3 or 4 times. So for third run, like it's provide initial gain, but just a couple of percent. But the second pass is very important. It's provide a big difference. So this may be not considered to be the fairest comparison toward HM and VTM. But anyway, I think the whole point here is to explore the potential. Okay, so this is more important.
Okay. Thank you, Dan.
Thank you.